Okay, Daniel Floryan is the Kelsey Assistant Professor of Mechanical Engineering at the University of Houston. He received his bachelor degrees in mechanical engineering and economics from Cornell University, and his master and PhD in mechanical and aerospace engineering from Princeton University, where he graduated as a Porter Ogden Jacobs Fellow. His research is at the intersection of fluid mechanics and nonlinear dynamics, with interests in bio-inspired locomotion and using data to model and control dynamical systems. With that, we are pleased to welcome Daniel and learn from him. So Daniel, you can take from here.
Okay, fantastic. Thanks so much for the introduction, and thank you everyone for coming to see my presentation this morning, afternoon, or evening, depending on where you are. And today I'll be talking about a topic I'm calling charting dynamics from data, and we'll see exactly what I mean from that. But before getting started, I just want to say a little bit about myself and my group. So as Sichang just mentioned, I'm an assistant professor at the University of Houston, and I just started in October of last year. So I thought it'd be worth describing a little bit about my group and sort of things that we're interested in. And I think the best way to do that is to just visit my website. So that's up here for anyone who's interested in it. And the sort of thing that our group works on is the intersection of fluid mechanics and nonlinear dynamics. And some of the topics that we're interested in include, they include things like bio-inspired locomotion. Other topics are learning structuring complex systems and how fluids and thermal effects interact with each other. And if you scroll to my website, there's also a page where I'm advertising positions. And so if anyone is interested in what I'm talking about today or some of the other topics that I just mentioned, or if you want to collaborate or even just have more questions, I encourage you to visit my website and also reach out to me via email. My email is here, dflorian@uh.edu, and I'll also post it at the very end. Okay, and I also want to acknowledge my collaborator, Mike Graham at the University of Wisconsin-Madison, who today's work was done with, and also the funding sources for today's work. So that's the AFOSR and ONR. So with all that said, let's get into today's presentation. And today's presentation is going to be all about dynamical systems. So dynamical systems are fundamental to our ability to model processes in engineering and the sciences. And an example that we're all familiar with is Newton's second law, which gives governing equations for how objects move. Another example that's become especially relevant in the last couple of years are SIR models, which are used to model disease spread and have been actually used during the pandemic to understand how coronavirus spreads. And there are many other examples as well where dynamical systems are really important to understanding what's happening in the real world. Now, with all this said, there are also a number of challenges. And some of these challenges are that the governing equations might be unknown or only partially known for a system that we care about. And it might also be that first principles derivations are not even possible to develop such equations. And even if we know the equations or can develop them, they may be so high dimensional to the point of being difficult to analyze and prohibitively expensive to make predictions with. And one example is shown here. So this is a computational mesh that's used for a global climate model from NASA. And you can see just how dense this mesh is and how high dimensional the system would be and how incredibly expensive it would be to actually solve the system of equations. So even in these sort of challenging situations where equations are unknown or high dimensional or incredibly nonlinear, we do often still have recourse to data. And so with this in mind, what our goal will be and what the theme of today's talk is to develop simple dynamical models directly from data. And the emphasis today will be on simplicity. Now, this doesn't actually get rid of the challenges that I mentioned on the previous slide. So even though we have data, data can still be incredibly complex and high dimensional itself. So how can we somehow use it to eschew these difficulties? So the key enabler here is that patterns often exist in data, especially in data that comes from dynamical systems. And I think this is really shown very well by this sort of video. So this is a video of flow over the island of Guadeloupe. And we know that weather and climate systems are very complex and high dimensional, but nevertheless, you can see this emergent pattern that develops in this incredibly complex system. And these sort of patterns enable low dimensional representations of dynamical systems, which allows us to develop simple dynamical models. Now, a way to sort of formalize this concept that patterns exist in data is to say that natural systems tend to at least approximately live on small manifolds or low dimensional manifolds in state space. And so here's the picture that I want you to have in your head whenever I say this. So let's say we have some state space, and I fill this state space with a bunch of particles. So I have a box of particles here, and you can think of each particle as representing the state of a dynamical system. Now, as I let these particles evolve forward in time under the dynamics, what we often see is that the state of a system is attracted to a lower dimensional manifold that's embedded in this larger space, in this case, to the surface of a torus. And this can even be true for infinite dimensional systems like the ones that we get from partial differential equations. And the key that makes this happen is dissipation. So when dissipation is present in a system, there often exists a finite dimensional attracting set that's called the inertial manifold. And it's this inertial manifold where the long time dynamics live. And so this sort of inertial manifold is what enables a low dimensional representation of the system. Okay, so with this in mind, let's go back to our original goal and make it a little bit more precise. So the way that we're going to achieve this goal is it by a two-step process. So first, what we'll do is find the manifold that's embedded in the high dimensional space. So you can think of it as finding this donut that we had on the last slide. So we will learn a coordinate transformation from the high dimensional coordinates to low dimensional coordinates that are valid on the manifold. And these low dimensional coordinates can be thought of as the essential dynamical variables. Then once we have the manifold, we'll then learn the dynamics on the manifold in the low dimensional coordinates. Okay, so we have two steps: finding the manifold and then learning the dynamics on the manifold. And there are many ways to learn a manifold. So I've listed just a handful of popular manifold learning techniques. And these are also ones that are sort of readily available in many well-developed software packages. And essentially what they all try to do is they all attempt to flatten a manifold. And so intuitively, the way that we usually think of a manifold is as some sort of curved surface that's embedded in a volume. And what nearly all these methods try to do is take this curved surface and try to flatten it out, in which case it's very easy to then come up with a low dimensional representation. But nearly all these methods encounter a serious problem, which is that the mappings that they come up with are not injective. And to give you some intuition for what that means, let's look at this torus on the right. So I'll color the top half of the torus in red and the bottom half of the torus in blue. And as we try to flatten this manifold or this torus, what you'll notice is that no matter which way we try to flatten it, we'll always get the torus collapsing onto itself. So let's say we try to squish it vertically, then what happens is that the blue and the red surfaces are now on top of each other. They coincide. And this means that the mapping is non-injective. And what it means is that we cannot recover the torus from the annulus. So now that it's flattened, we can't actually differentiate the blue from the red since they're at the exact same points. And so we can't actually reconstruct the torus from this flattened space. And this is a problem because you've now lost information. You can't go back and forth between the two representations, which is key to actually have a good representation of the manifold. So in order to fix this problem, we'll have to understand what manifolds are a little bit more deeply. And so I'll keep working with this sort of torus on the left. And the way that we'll represent a manifold is as what's known as an atlas of charts. And I'll explain what each of these words mean in the context of manifolds. So a chart is something that has two ingredients. It includes an open subset on the manifold that's called the coordinate domain. So think of it as this red or pink piece of the manifold, as well as a continuous invertible map that takes us from the coordinate domain, from this pink piece of the manifold, to a subset of a Euclidean space of the same dimension. And what you can think of this mat phi as doing is it's taking a piece of the manifold and just flattening it out. And then what an atlas is just a collection of charts whose coordinate domains cover the manifold. So in addition to this red one, we might have a blue one, and you can keep adding more and more until they cover the entire manifold. Okay? And a key property of these things, which will be especially important for dynamical systems, is that we can transition between the low dimensional representations where they overlap. And so really the way to think of a manifold is as a collection of patches that can be flattened. So instead of trying to flatten the whole thing in one go, you sort of break it up into pieces, each of which can be flattened. And not just flattened, but also invertibly flattened. So you can go back from this flat representation back to the surface of the manifold. And this representation is minimal dimensional. Okay, so really sort of breaking things up into patches is something that allows for a minimal representation of the manifold. And this sort of idea of breaking things up into patches is something that will solve the problem that we saw on the last slide. So if we go back to our torus, decomposing the manifold into pieces solves the problem. So now that we, instead of working with a whole torus at once, what we'll do is first break it up into a few pieces, in this case, 6 pieces. And then each of these pieces can be separately flattened. And we can also go back from these flattened pieces to our manifold. So now in this case, instead of having sort of this embedded 3-dimensional representation of the surface of the torus, we've gone from that to a collection of 2-dimensional representations for each of these patches. And so we've gone to this sort of minimal dimensional representation of our manifold. Okay, so this is really the main idea behind the talk today, sort of breaking things up into pieces and then working with each piece individually and then sewing the pieces back together to get a global representation. But how can we actually implement this approach when all that we have is a collection of data? So this is how we're going to implement this idea of an atlas of charts. So we'll assume that we're given a time series of data. It can be either one long time series or several sets of smaller time series. And we'll assume that the data lie on or at least close to a manifold. And then we follow a 3-step procedure. So in the first step, what we do is cluster our data into overlapping patches. So if you look at the torus on the left, we have several data points in black dots. We cluster the data. Let's say this is the first cluster that we come up with, the red dots. And these red dots, or these clusters, sort of implicitly form our coordinate domains. And for everything that I'm showing today, I'll be using the k-means algorithm for the clustering, and then an additional procedure to make the resulting clusters overlap with each other. Okay, so now that we have a patchwork representation of the manifold, the next step is to learn how to flatten each patch. And the way that we do that is for each patch, we approximate the coordinate map phi that takes us from the high dimensional space to the low dimensional space. And we do this, at least today, we'll be using neural networks to do this. So neural networks are good function approximators. And so we'll use them to approximate this function phi that flattens our manifold. And simultaneously, we also learn the inverse of this mapping. So we use another neural network to approximate the inverse of this mapping. And you might notice that this sort of takes the form of an autoencoder, where we have this mapping phi that reduces the dimension, and then its inverse that takes us back to the original space. Okay, so at this point, what we have is a patchwork of our manifolds and a way to flatten each patch. And so the last piece now is to deal with the dynamics. So the way that we do that is for each patch, we now have a time, we now have time series data in the low dimensional coordinates. And we learn the dynamics from these lower dimensional time series. So the dynamics are still nonlinear in the low dimensional space. And so we train neural networks to either learn ordinary differential equations or time delta t flow maps in this reduced space. And we'll use, again, a neural network today to represent the dynamics in this lower dimensional space. And at least for what I'm showing today, the dynamics will be in the form of time delta t flow maps. So they'll sort of take your state and then map it forward some time delta t. But you could also, instead of learning these finite time flow maps, you could also learn differential equations for the dynamics. That's not a much more complicated step. Okay, and this is the whole method that we'll be using today. So I mentioned autoencoders, so maybe I'll just briefly describe what they are. So what autoencoders do is they take a high dimensional input, map it through this sort of bottleneck in the middle where you have a low dimension, and then map back out to the same dimension as the input for the output. And so the idea here is that you try to learn a reduced representation of your input. So if you have a cat as an input, you want to learn some essential or reduced representation of that cat, and from that be able to get the full cat again. And so we're using this for the manifold learning step in our procedure. Okay, so with all that said, I just want to take you through a handful of examples that demonstrates what this method is capable of doing. So I'll start with some really simple examples, simple periodic dynamics, and end with a pretty difficult example of PDE with intermittent dynamics. And again, what we're trying to do is learn the simplest possible representation of each of these dynamical systems. And what I'll show and hopefully convince you of is that this method that I've outlined for you, where we're breaking things up into local representations, gives us new capabilities that other methods cannot give us. Okay, so let's get to our first example. So this will be a really simple one, which is just a particle moving around a circle. So imagine that we have a unit circle and we have some particle that's moving around it counterclockwise. And nominally, this is a two-dimensional system. So to describe the position of the particle, we need an x coordinate and a y coordinate. So that's why it's two-dimensional. But we know that a circle is really a one-dimensional object, right? So if you sort of zoom into a piece of the circle, then a piece of it is just a one-dimensional curve. And so we should be able to come up with a one-dimensional description of this very simple dynamical system. And we're going to use our procedure to do that. And the data that we have will consist of 40 points, just equally spaced along the circle, that correspond to one revolution around the circle. So let's see how this works. So we'll just follow our procedure step by step. And the first step is to form overlapping patches of this circle data. And that's shown at the left here. So we break up the circle into 3 patches, and this is done automatically with the k-means algorithm. So you can see a red patch, a blue patch, and a yellow patch. And we also make sure that these patches overlap with each other. Once we have each of these patches, we then train autoencoders for each of these patches to find a reduced representation. And again, what these autoencoders are doing is basically flattening out each patch. So we go from this sort of curvy piece of a circle to just a straight line. And the straight line can be represented in one dimension. So there's only one coordinate to keep track of for each of these line segments. And we also, again, learn the inverse of this map. So we can go back and forth from this curve to a straight line. And then once we have this low dimensional, in this case, one-dimensional representation, we then train neural networks to learn the dynamics in the reduced spaces. Okay? And that's represented by these arrows in panel C, and the maps F1, F2, and F3 that tell us where the dynamics take a point in each of these coordinate systems. And in the end, what we're left with is a correct minimal dimensional dynamical model with smooth transitions. So what I'm showing on the far right here is what happens when you take some initial condition that's on the circle and then just evolve it forward in time under our learned dynamical model. So here our learned dynamics are just one-dimensional, represented in each of these patches. And the individual points show how the system evolves forward in time with our learned model. And you might also be able to see, or hopefully you can see a solid gray line on top of these points. So that solid gray line, that's the true dynamics of the system. And you can see that our learned model follows the true dynamics very closely. And what I especially want to note is how smooth the transitions are from one chart to another. So as you change colors, that transition is a very smooth one. Cool. Okay, so let's get to a slightly more difficult example. And maybe just for the sake of time, I'll skip ahead by one example. So here, in this example, we have a slightly more complicated system. So what we have is a particle, but now instead of moving around the circle, it's moving around the surface of a torus, or the surface of this donut. And the way that it's moving is that the toroidal, or the speeds in the toroidal and poloidal dimensions are incommensurate. And what that means is that if you just let this particle move around this torus forever, then it'll eventually densely cover the surface of the torus. And this incommensurability between the toroidal and poloidal speeds leads to quasi-periodic dynamics. And these, again, orbits that densely fill the surface. So nominally, this is a three-dimensional system. So we need X, Y, and Z coordinates to describe the position of the particle on the surface of the torus. But really, we know that it's a two-dimensional system because we know that we're just on the surface of this torus. So we should be able to come up with a minimal two-dimensional representation of this system. And to do so, we follow the same procedure as we did for the circle. So first we break this torus up into different patches. So in this case, using 6 patches, red, blue, and yellow, green, purple, and orange. And each patch, we then map it to a two-dimensional space, or we take each patch and we flatten it out. okay? And that's shown here. And again, this mapping is invertible. So we can go from the 2D flat representation back up to this curved representation embedded in 3-dimensional space. And again, once we have the low dimensional representation of each patch, we then train a neural network for each chart to learn the dynamics for each of them. And in the end, here's what the dynamics end up looking like. Okay, so let's first focus on these top 2 plots on the right in panel D. So what we're doing here is, again, taking some initial condition that's on the surface of this torus and then evolving it forward in time using our learned dynamical model. So here I'm showing, on the first 2 plots, I'm showing the X, Y, and Z coordinates, the dynamics of those using our learned dynamical model. And on the bottom 2 plots, I'm showing reconstructed versions of the 2 angular coordinates, the toroidal and poloidal coordinates. And there you can really see how good the dynamics are that we've learned. So the colored points represent the dynamics of our learned model, and the solid gray line represents the true dynamics of the system. And you can see that, again, the dynamics that we're capturing are quite accurate. And even as we go out to many time steps forward, so in this case, up to 1,000 time steps out, we see that we still have a very good representation. So, one of the angular speeds that we've learned is a little bit faster than the true system. So you can see that these triangles here are shifted to the right of the solid gray line, and then the bigger ones are a little bit slower than the solid gray line, but we're getting very accurate dynamics, and most importantly, we're getting correct quasi-periodic dynamics. And again, the key thing here is that we've learned a minimal representation of our system. So we've learned a minimal 2-dimensional representation of our dynamics, and this is something that you cannot do using any other method. So again, breaking things up into separate patches like this has enabled the simplest or most minimal dimensional model possible. Okay, so let's get into something a little bit more complicated than just circles and donuts. And so what we'll do now is work with dynamics from a partial differential equation. So the PD that we'll be using will be the Kuramoto-Sibishinsky PD, which I've written here. And this is a PD that among other uses, it's used to model flame front dynamics. So the evolution of flame fronts, just a few snapshots shown on the bottom left here. And there's also a parameter in this equation. You can see that's this parameter nu in the last term here. So this is a hyperdiffusion coefficient, and changing its value sort of changes the balance between convection, anti-diffusion, and hyperdiffusion, and changes the sort of dynamical behavior that you can see. So this is a system that has really rich dynamical behavior, and we'll see several examples of that. So in this first example, we'll use a value of this parameter nu that gives us beating dynamics for this PD. And that's shown here. Okay, so you can see that. Okay, so what I'm showing is a space-time plot. So space on the vertical axis, time on the horizontal axis, and the color corresponds to the U in the equation. Okay, so you can see as we're moving forward in time, so as we're moving from left to right, we get these this beating periodic dynamics in our system. And in this case, we've solved this PD using the pseudospectral method with 64 Fourier modes. So for this case of beating dynamics, nominally the system is 64 dimensional. That's the number of degrees of freedom that we had to use to solve the system. But we know that really we should be able to get a 1-dimensional representation of it. Right? So because we have these periodic beating dynamics, sort of what you should see in state space is equivalent to a circle. It's just this sort of periodic dynamics. And so we should be able to use the method that we've outlined previously to develop this one-dimensional model. Okay, so this is the data that we're dealing with here, one time unit of the dynamics here. And the colors at the top, the red, blue, and yellow colors just above the space-time plot show the result of applying k-means and patching this up into 3 different patches. Okay, so in panel B, this is the data reconstructed from a one-dimensional representation. Okay, so for each of these patches, we train an autoencoder to learn a one-dimensional representation, and then we can map back from those 1D representations to the full 64-dimensional space, which is shown in the second space-time plot. And again, we just keep following our procedure, and in each of these low dimensional, or in this case, one-dimensional representations, we then learn the dynamics. And the result of doing that is shown here below. So again, what we're doing is we're starting with some initial condition and then evolving forward in time using just our learned dynamical model. And you can see that our learned dynamical model is incredibly faithful to the true dynamics. So this whole space-time plot on the bottom, that is, we get that just from a one-dimensional representation of our system. And you can see how we're switching between patches, between red, blue, and yellow patches from these colored bars on top of the space-time plot. And the period is dead on with true dynamics, and the magnitude of the field is as well. And so again, using this method that we've outlined, we're getting an incredibly faithful, minimal dimensional, in this case, one-dimensional representation of the dynamics. Okay, so now what we'll do is we'll go on to a slightly more complicated example. So we change the hyperdiffusion coefficient in the PD. And when we do that, we now get beating traveling dynamics. So if you look at the top row, you can see that there's this very slow drifting behavior that occurs over approximately 100 time units. And if you zoom into a much smaller time window, which is shown in the upper right here, you can see that we also have this much faster beating dynamics, okay? And so the beating period is about 0.5 time units, and this sort of drifting period is about 100 time units. So now we have these 2 very disparate time scales. So now we're sort of dealing with this multi-scale problem. Okay, so a special thing about this system is that there is a translation invariance that's present. And so we'll actually take advantage of that symmetry in coming up with our model. And the way that we're going to do that is to first decompose this data into shape variables and phase variables. And so that's represented by the next 2 rows. So the data that we have is this top row here. And if you separate it into shape and phase variables, then you get the middle row and the third and the bottom row. So the middle row is just the shape of the data. So you can think of it as we've basically taken the drift out, and then we represent the drift by using this phase variable in the bottom row here. Okay, so we've separated the data into a shape variable and a phase variable. And then from this sort of separated data, we learn our model. Okay, and so here is the data that we actually have. It's just one time unit of data. This is all that we feed into our algorithm. And we follow the same steps that we did before. So we cluster this one time unit of data into 3 clusters in state space. And then for each of those, we learn a simple representation. So for the shape data, we can just learn a one-dimensional representation, which is shown on the top right here. And in panel B, that's showing the data reconstructed from the one-dimensional representation. And then in each of these low-dimensional coordinate systems, we then learn the dynamics there. And in the end, this is what we get. So again, what we do here is we start with some initial condition and then evolve it forward in time using just our learned dynamical model. And you can again see that we're doing a very good job of representing the true dynamics. So we have this sort of very slow drift over nearly 100 time units that you can see. And if we zoom in to just one time unit of our modeled system, you can see we're also getting the much faster beating dynamics very accurately as well. And I just want to emphasize here that we only used one time unit of data to train our model. Okay, so if you look at this bottom plot here, we basically only used 1/100th the size of this to train our model. And nevertheless, we can very accurately capture not only the beating dynamics, but these much slower drifting dynamics as well. And this is enabled by both our representation of the system in terms of patches, and also by factoring out this translation, these translational equivariance symmetry that I mentioned previously. And in the end, we get this minimal dimensional, one-dimensional representation, or really two-dimensional representation, since we also learn the phase dynamics of our system. Okay, so the last example that I want to show you is a PD with even more complicated dynamics. And so in this case, we'll have intermittent dynamics. So here's what the space-time plot looks like. So you can see that we have sort of these quiescent periods, or where we have a cellular structure, and then we sort of rapidly switch between one cellular pattern and another one. Okay, so we have these periods of quiescent, nearly steady behavior, and then very rapid switches to another period of steady behavior. And maybe to give you some more intuition for what the dynamics look like, here I'm showing a state space projection. Okay, so projection onto the first 3 Fourier modes. And this red dot shows what the system is doing. You can see that what's happening is it's basically sort of bouncing back and forth between these two saddles in a very intermittent fashion. So it's sort of staying near a saddle for a long time and then bouncing to another one. And it's doing so by basically randomly choosing one of these homoclinic connections. And so the key challenges in this example are that it's very high dimensional, so or at least mildly high dimensional. So in this case, we used 64 Fourier modes to numerically solve this PD. It has disparate time scales, so these fast bursts between quiescent scales. And it has a very thin state space structure. So that's shown by this state space projection, where you can see a very thin structure. And the dynamics are sensitive and non-periodic. So I mentioned that the sort of bouncing back and forth between these two saddle points happens along sort of random choices of these homoclinic orbits. Okay, and so this is a very challenging example. It's actually an example that we tried several methods on, and none of the classical methods were able to develop or to come up with a good dynamical model of the system. And so we'll see how the model that I've presented today works. So we followed the same procedure that we did for each previous example. So we first take our data and then cluster it up in state space. So in this case, we broke this up into 6 clusters, a red one and a blue one that pretty much correspond to these saddle points in state space. And then yellow, orange, purple, and green patches, which basically correspond to these homoclinic connections between the two saddle points. So now that we've broken this up into 6 patches, we then follow our procedure to learn an atlas with 6 charts. And I should also mention that for the dimension reduction step, we use these special autoencoders that combine principal components analysis together with neural networks from this paper in PRE by Lynett and Graham. And when we do that, here is the model that we end up learning. So the space-time plot that I'm showing on the bottom left, what we've done is taken an initial condition, and then we evolve it forward in time using our dynamical model. And I've also shown the state space projection of that resulting data. And so you can see that what we get is a qualitatively correct minimal dimensional model. We have these quiescent cells with fast bursts between them. But you can see that there is a quantitative discrepancy in the length of the quiescent periods. Right? So comparing the bottom to the top, you can see that the quiescent periods on the bottom are not as long as the quiescent periods up top. But this is something that we believe is inherent to the system. So, so you can show that there's the sensitivity to model error. We attribute that to a logarithmic divergence that's associated with the saddle points. And so it's not something that we believe is a problem with the method itself, but sort of the dynamics of the system. So this is something that we believe you'd basically get this sort of behavior with any technique that you use to learn a dynamical model. But in any case, we do get this qualitatively correct and nearly quantitatively correct dynamical model that's minimal dimensional, so just 3-dimensional in this case. Okay, and so the last thing I'd like to do here is just to compare this to previous methods. And in particular, there's a theorem, a mathematical theorem that's especially relevant for this comparison, and it's known as the Strong-Whitney embedding theorem. And what this theorem tells us is that if we don't use an atlas of charts, so if we don't break things up into patches, we should still be able to reduce the dimension of our system to 2n in the worst case. And so for this system with intermittent dynamics, where we were able to learn a 3-dimensional model when we were using patches, if we don't break things up into patches, then we should still be able to learn a 6-dimensional model with the same level of accuracy. And here's what you get when you try to do that. Okay, so the gray curves show the true manifold or the true attractor of the system. And the blue curve shows the dynamical model that you get when you try to learn a 6-dimensional model without breaking things up into patches. And we consistently get this sort of behavior, which is completely qualitatively incorrect. So even though Whitney's theorem is telling us that we should theoretically be able to get the correct behavior, we consistently are unable to get it. And this is revealed even more when we look at the reconstruction error. So this is the reconstruction error. So how we're able to reconstruct the data from the low-dimensional representation that we learn. And here, these colored points, they show the reconstruction error when we break the data up into clusters. And the white and black points show the reconstruction error when we don't break things up into clusters. And I want you to pay attention to the points that are circled in green and the points circled in gray. So the points circled in green, these correspond to the reconstruction error of a 3-dimensional model when we break things up into patches. So this is the model from the previous slide. And then the points in gray, those are the reconstruction error of our 6-dimensional model where we don't break things up into different patches. And these two sets of points, the one circling green and gray, they have the same number of trainable parameters for all of the neural networks. And the points in gray have a dimension that's twice the points in green. So sort of corresponding to what Whitney's theorem is giving us. But nevertheless, you can see that when we break things up into patches, we get an order of magnitude better reconstruction than when we don't break things up into patches. So even though Whitney's theorem is giving us a mathematical reason to believe that we should be able to do just as well without breaking things up into patches, you can see that in practice, breaking things up into patches is actually giving us some benefits beyond what might be theoretically expected. And so this sort of decomposition into patches is giving us performance beyond, even beyond what we might expect based on this mathematical theorem, Whitney's embedding theorem. Okay, so we're getting not just the ability to learn a minimal dimensional representation, but also additional practical benefits that allow us to learn more accurate models. Okay, so just to quickly summarize, inspired by differential geometry, we developed an atlas of charts-based approach to learn the simplest dynamical models possible directly from data. And the way that our approach works is by learning a patchwork of local models and then sewing them together to get global dynamics. And as we've shown, this sort of breaking things up into patches, it unlocks abilities that global methods do not have, at least for the problems that we've shown here. And there are three major benefits that I want to highlight to this method. One is the ability to obtain dynamical models of the lowest possible dimension. Second is a divide and conquer approach that leads to computational benefits, including scalability, the ability to adapt models locally, and an embarrassingly parallelizable algorithm. And the third one is the ability to separate state space into regions of distinct behaviors. So this is something that we think would be particularly suited to bursting and intermittency that's characteristic of turbulent fluid flows, for example. And I also just want to briefly note that even though we use neural networks for the work that I showed today, those aren't actually required. You can use any other sort of regression framework that you like. Neural networks were just a convenient choice for what I showed today. So with that, I'd like to thank you very much for your time, and I'd be happy to take any questions that you might have. Thanks.
Yes, thanks, Daniel, for sharing with us. It's really fundamental research, like using the geometry in the dynamical system. It's really, really interesting. Is there any question from the audience? If there, okay, I saw a question. You can either ask in the chat or directly ask Daniel. So, Sam Boo asked a question. So I have got to. Oh, yeah, I just want to thank you. So, yeah, Giovanni, you can unmute yourself.
Hi, I thank you very much, Daniel, for this terrific presentation. I really like that. I have a number of questions, but I don't want to ask all of them. Just perhaps I'll start with one. And if there is time, perhaps continue with a couple
Sure.
more questions. Yeah. One thing that I would like to ask you is about parameters involved in your in this framework. So, for example, the dimension of the low order, let's say, space is something that you have to set. Like, for example, you mentioned the example of from 2-dimensional to 1-dimensional. Okay. So you should know that that is a 1-dimensional motion, or the autoencoder is able to infer the low-dimensional, the order of the low-dimensional space.
Yeah, so that is something that that is information that we have to provide manually, and this is true of nearly any dimension reduction technique where you have to provide the dimension that you want to reduce to. So in a lot of these examples, I knew what the answer was, right? So for the circle, for example, I know that that's a 1-dimensional object, so I can just do that directly. For the last example that we showed, which was this guy here, So here we actually did not know what the dimension was ahead of time. And so that's something where we had to iteratively come up with the dimension of the system. So we don't know it ahead of time. We don't really know the true dimension, but based on the model that we learned, we suspect that the true dimension is 3. And so again, this is something that you sort of iteratively have to guess as you would for any use of an autoencoder. The nice thing here is, normally when you have to guess the dimension that you want to reduce to, you guess the dimension and then you try to reduce the entire data set to that dimension, right? So you have to apply your method to the entire data set, which could be expensive if you use all of your data. But by breaking things up into patches, what you can actually do is sort of iterate the reduced dimension of your system on just one patch. So the dimension of a manifold, that is a global property. Okay, so the entire manifold has the same dimension everywhere. And so if you break things up into patches, each patch must have the same dimension as every other patch. So what you can do is iteratively find what the dimension has to be by only using one patch of the data. And that makes things less expensive than if you try to iteratively reduce the dimension of the entire data set. And so that's one additional benefit that you get out of this. So as you iteratively try to find the correct dimension to reduce to, you can do that using less data.
Okay, thank you very much. I have another question. I don't know if there's anyone else out there want to ask something.
I guess you can go ahead. There's no.
Yeah. Meanwhile, I was wondering. I mean, my guess is that you use a k-means algorithm with overlapping, because overlapping somehow connects the patches together. So in order to have a link between patches, not just being independent clustering. But I was wondering how the size of this overlapping can impact on the result.
Yeah, so that's correct. So I guess there are 2 reasons for the overlapping. One is that that's actually how a manifold is defined, as a collection of overlapping pieces. And so we're trying to remain faithful to that mathematical definition of a manifold. But more practically, the more the manifolds overlap with each other, the smoother the transitions you get in your dynamical model as you go from one patch to another. And so we've played around with how large we make this overlap. And in that case, basically the larger the overlap is, the smoother the transition is from one chart to another. Okay. And so that's the sort of practical reason why you might want to have a greater overlap between patches. But again, you don't want to make the overlap so big that you end up having, patches that are themselves quite large and end up closing on top of each other. So that's, the thing to weigh.
Yeah, okay. I think in the chat there are a few questions, so just leave the floor to other questions. Just one question. There is a code out there that it can be downloaded for this framework?
Yes. So
okay. I'll take a look at that.
Yeah, if you go to my GitHub,
great.
There's a repo there.
Thank you very much.
Yep.
Okay, so there's a question from Savis Molev. Sorry for my pronunciation. So thanks for your talk. I have 2 questions regarding the clustering part. First is, in which space do you apply the k-means algorithm? Original space of the snapshots or some POD reduced space? And the second question is, how do you decide the number of clusters? I guess it's kind of related to Giovanni's question. So,
yeah. So, okay. So the clustering, we always apply that in state space. And for all the examples that I've shown here, that's been in the full state space. So not reduced by any POD procedure. Now, if you have a system that is very high dimensional, then what you could do first is, let's say, reduce the dimension of something that's super high dimensional to something that's a bit lower using PCA or POD or some other linear dimensionality reduction technique. and then do the clustering in that mildly reduced dimensional space. So that's what we do there. Could you remind me of the second part of the question, please?
The same question is, how do you decide the number of clusters?
Okay, yeah. So that is something that we have to do manually, at least now. So for a lot of these examples, I sort of knew how many I could use, like what was the minimum number that I could use. And I used that information. But in the last example, in this one, here we did not know how many we needed ahead of time. But we used this sort of exploratory data analysis where we looked at state space projection onto the leading Fourier modes to guess how much we needed. So when we look at this state space projection, you can see that the structure of this data is that we have these two saddle points and these four homoclinic connections between the saddles. And based on this, we thought that 6 clusters would be an appropriate number to use. So one for each of these saddle points, and then another one for each of the connections between the saddle points. So in this case, that's why we chose 6, and that choice was based on this exploratory data analysis. What would you do for a more complicated system? So that's something that you would probably have to iterate. Maybe potentially a good way to go about it would be to first start with a very large number of clusters. And if you have a very large number of clusters, then in principle, this should work anyways, as long as your sort of clusters are, as long as they don't close up on each other, then this method should work for any number of clusters. But from a practical standpoint, you could start with a very large number of clusters and then keep reducing that until you see, that you're not able to reduce the dimension to as low of a dimension as you'd like. So again, it'd be sort of a manual iterative process to get an appropriate number of clusters. And the balance here is you want clusters that have enough data where you could train accurate models, right? So you need clusters that are big enough to have accurate models, but you don't want them to be so big that they're actually closing up on each other, in which case you wouldn't be able to reduce the dimension as much as you'd like to. So that's the balance that you have to play with.
Okay, and I have a question. So I saw you use a KS model. So I guess a natural question is, can this atlas and chart method be applied to chaotic dynamical system?
Yeah. So this last system actually is chaotic.
Oh, it's chaotic. Okay.
Yeah. But we are trying this on some higher dimensional and more complex systems. So right now I'm trying this, or I'm working on this for Rayleigh-Bernard convection. Mm-hmm. A postdoc in Mike Graham's group is trying this out on a turbulent flow problem. And we've also started thinking a little bit about trying this method out on real world data. So I believe it's like sea surface temperature data in the real world. And so, in principle, everything should work.
Yeah.
I guess we'll see if it actually does work.
Yeah, nice. Is there any more questions from the audience? Yeah, I guess that's all questions we have today. And I want to thank Daniel again for sharing with us this really nice work. And guess we will meet you next week. Right. See you guys.
Okay. Thanks so much, everyone.
Thank you. Yeah. Bye.